In this video, we'll talk about geometric and recursive sequences, which are two of the main types of sequences that you will see both in this class and beyond them. So geometric sequences are sequences that have a certain form of function that defines every value of the sequence. And what is that form? Well, these are sequences of the form an equals some constant times some ratio to the n. For we'll say n bigger or equals 0, but you can use bigger or equal 1, whatever we want to start it at is fine, but it's sequences of this form. So something like an equals 2 times 3 to the minus n, that's of this form. Your r here is 1/3 because that flips it over. Something like bn is 1/2 5 to the n is also a geometric sequence of the same form. It's a constant times a ratio to the n, and that's how you write out these terms. So for instance, for this an over here, a1 would be 2 times 1 over 3, which is 2/3. A2 would be 2 over 9. A3 would be 2 over 27, and so on. Now I want to look at, do these sequences have limits, and if so, what are they? So to do this, we have to look at the limit as n goes to infinity of c times r to the n. And we can think about this now in terms of the function version as well, because this should behave like the limit as x goes to infinity of c times r to the x. Now, what happens to r to the x as x goes to infinity? Well, this depends on the value of r. If r is less than 1 and bigger than 0, then it's something like 1/2 to the x power, and that's going to go to 0 as x goes to infinity. Because I'm raising a number less than 1 to a power, so 1/2, 1/4, 1/8, 1/16, that's getting smaller and smaller as x gets bigger. And so in that case, the limit as n goes to infinity of c r to the n is also 0. The geometric sequence goes to 0 if r is between 0 and 1. If r equals 1, then this is just c for all x and c for all n, so the limit as n goes to infinity of c times 1 to the n is just c. It's always c. And if r is bigger than 1, then c r to the x goes to infinity, so this sequence diverges. You can also do this by plugging in some numbers to see what happens. If the r is less than 1, then it's going to go to 0. If it's bigger than 1, the number is going to get bigger and bigger and bigger as you multiply by more and more numbers. The sequence is going to diverge. This will be important when we're going forward to talk about series in the next section. Now, the other main type of sequence you can see is one where it's not given by an explicit formula, where the terms are given recursively. And what does this mean? This means that every term of the sequence is defined in terms of some previous terms and not given a formula on its own. So a brief example of that could be something like define a1 to be 1, and then an is 3 times an minus 1, for n bigger or equal 2. So the point here is I have no way of getting, say, a5 directly, at least not from this formulation. I have to step through each term one by one to get up to a5. What does that look like here? Well, if a1 is 1, then a2 is 3 times a1, which is 3. a3 is then 3 times a2, which is 9. a4 is 3 times a3, which is 27. And then a5 is 3 times a4, which is 81. You might see the pattern here, and that's a pattern you could, in some sense, prove with methods that we're not going to cover in this class. So here's an example of this. Find the first 5 terms of the sequence defined by a1 is 2, a2 is 3, and an plus 2 is twice an plus 1 minus an for n bigger than 1. So we just need to figure out what a3, a4, and a5 are. Since we don't have an explicit formula, it's defined recursively, we have to do this step by step. So then what is a3? Well, based on my formula here, a3 should be twice a2 minus a1, which is 2 times 3 minus 2, which is 4. a4 should then be twice a3 minus a2, which is 2 times 4, the 4 that we got from right up here, minus a2, which is 3. That's 5. a5 should be twice a4 minus a3, twice 5 minus 4, which is 6. And you could think maybe there's a pattern here. Maybe it is the case this is just linear going up every time. It turns out that is the case, but that's nothing we can actually prove here with what we know so far about sequences. The point here is you can determine what the terms all are using the previous terms in the sequence. So that's the idea of both geometric and recursive sequences and how they look and how they behave when you're thinking about sequences. You'll see things like this come up when we're talking about stuff later in this section and stuff with series later on, but it's important to have the basic idea of what these things are before we go forward into those topics.